Good day, everyone. Thank you, Gediminas, for the kind invitation. Maciek too. On a personal note, I have to say that my family came here 150 years ago, okay? Which makes us, I would say, one of the old-timers of this city. And we left it 60 years ago, when I was 6 years old. I'll be 66 this year. It has some meaning to me to be here, second time actually. I would like to tell you today about the comparison between classical and quantum thermodynamic machines, or at least machines that are claimed to be. If there are indeed different rules in the quantum domain, does this imply that machines can be better than their classical counterparts by virtue of being quantum mechanical? So we all know the Carnot bound, which is that the output work divided by the input heat is bounded by 1 minus the cold bath temperature over the hot bath temperature. And one of the claims which actually got this started was that one can do better than that by quantumness. The more general question is, what happens if you replace one of the ingredients of a basic heat engine by a quantum ingredient, okay? Will that indeed, or can it indeed, improve the efficiency? Or if not the efficiency, then at least boost the power. There have been claims to both of these results. It's now called quantum advantage, and some call it quantum supremacy. Are any of you quantum supremacists? Okay. The point is that in this series of papers we have shown that one has to be very careful when using such notions. So the first claim that actually got this going was by my old mentor, Scully. I mean, old not in the sense of age, but what Scully and co-workers showed was that if you have a Carnot engine, okay, in which the working fluid are, say, photons, and they are powered by a hot bath of a special kind. This is actually a variety of the micromaser, for those familiar with it. Now, Scully's point was that if you replace your usual thermal atoms in this bath by atoms he called phasonium, in which the lower levels have coherence between them, then you can obtain a boost of the efficiency above the Carnot bound, depending on the cosine of the phase between these two levels. Now, this sounds strange, but we have checked, and it is perfectly correct. The question is whether it contradicts or transgresses in any way the standard assumptions of thermodynamics, and we contend that it does not. The reason being is that from the point of view of the working fluid, there is a thermal bath at a temperature which depends on the cosine of phi, okay? So the working fluid doesn't know any better. If this is the hot bath temperature which it receives, then it obeys the Carnot bound, but with this phase dependence, which is of course curious, but there is nothing that contradicts thermodynamics to it. But then, a few years later, a different claim was made by Eric Lutz, And that was that if you take an engine, say a Carnot or Otto engine, and you replace the thermal bath by, say, a squeezed bath, okay, in which you have both temperature and squeezing, to be general, then you can exceed the Carnot bound. In fact, the basic effect was even demonstrated experimentally lately by Imamoglu. Now, this is, again, a claim that has to be scrutinized, not because it is mathematically wrong, but because of what it means. And finally, there is a notion, Seifert is one of the people that stand behind it, that you could boost power in a heat engine by means of quantum coherence. So take a 4-cycle engine, and in which you have decompression and compression alternating and contact with hot and cold baths alternatingly. Look at the quantum equivalent of such an engine. And this could be a Bloch sphere which undergoes compression and decompression corresponding to change in the splitting between the levels. That would be the equivalent of these 4 classical strokes and would correspond then to the extraction in their language of classical work. But in addition, you could have a rotation of the Bloch vector, okay, which would be associated with coherence. And this, they say, is an extra source of work, which they associate with quantumness. Okay? Again, the question is whether such an interpretation is valid. So that led us to the conclusion that one needs a comprehensive theory that would explain what work and what heat actually mean in the quantum context. For that, one has to revisit the first law of thermodynamics, which corresponds to the explanation of energy exchange between a system and the bath. The question is how one decomposes such energy exchange into heat and work. Now, the pioneering work here was made by Alitsky in '79. He identified heat with the time derivative of the state of the system, okay, and work with the time derivative of the Hamiltonian. Seifert and the others have gone even further, and they decompose this work, or rather its derivative, into a sum of terms which are associated with the diagonal elements of the state in the energy basis, rho n, okay, E dot n. And this they identified as this classical work, which corresponds to changes in level splitting. But in addition, there are off-diagonal terms, okay, which they consider to be purely quantum. Now, there is a problem with this entire decomposition, and the problem is the following. Let us take a very simple example. By the way, I'm lost as to how much time I have now with all this mess.
You have 10 minutes.
Okay, thank you. So, suppose that we start a cavity in a coherent state and let this field leak out of the cavity so that in the end you have an empty cavity. You started with a pure state, you ended up in a pure state, and therefore entropy hasn't changed by any, I would say, physical argument that you may invoke. However, the energy definitely has changed, and according to Alitsky's decomposition, this should correspond to heat. just because it is energy change. So this is a problem. And so is, for example, the case in which you start an atom in the excited state, it decays down to the ground state, and in both cases you have pure states, entropy hasn't changed, and yet definitely energy has changed, has gone to the bath. So what's the problem with these examples? And oddly enough, the solution was given also by Poles, Pusch and Voronovich, in '78. They distinguished between so-called passive and non-passive states. Now, this is an illustration. Suppose I give you a battery with the same amount of energy in it, okay, in all three cases, and I connect it to a bulb. In one case, I see that the bulb is lit very dimly, and I call this partly non-passive state. In the other, it doesn't light at all, okay? I call it passive state. And here it is lit very brightly, and I call it a fully non-passive state. So what differs between these three states is their non-passivity, or as some people call it, ergotropy. What does it mean? Mathematically, it means that I take my state, okay, say this is the distribution of eigenvalues in the Fock space, and I perform a unitary transformation which reshuffles the eigenvalues so that they are monotonically ordered. This is the state with least energy that can be attained unitarily from a given state, and this state I identify as the passive state. This is a unique transformation. For each state, there is just one passive state. The energy which I obtain in the process is the amount of work or ergotropy which is stored here. So by the time I'm in a passive state, I have no more work to extract. And in the phase plane, the equivalent of a non-passive state would be a displaced phase space distribution, whereas a passive state would be a phase space distribution which is centered at zero. Okay. Now, that has led us, and here Wolfgang Niedenzu, my postdoc, was the main proponent, to the following result, which we call reformulation of the first law. In fact, one has to divide the energy which is exchanged between the system and the bath into heat and work as follows. Heat exchange is only associated with a change in the passive state, which corresponds to the actual state that we have. So we have to perform a unitary transformation that gives us a passive state, and then whatever is left, which is associated with the change of that state, that is genuine heat. Now, this has implications for the second law, because Spohn in '78 has written an inequality for entropy change, which said that delta S is bounded by the total energy which is exchanged between the system and the bath. And as we now know, part of it corresponds to heat, but part of it corresponds to work, okay? Not to heat, all right? And of course, this cannot be the best estimate for delta S, or rather for the reversibility condition, which is delta S equals 0, because it contains this unitary part that has no significance as to entropy change. So instead, what we say is that one has to identify delta S only with the genuine heat exchange, as written here. And this is the inequality which we propose for it. Now, this has strong implications for the performance of machines. Because if we are now coupled, as in the Lutz proposal, to a non-thermal bath, then what we'll receive from the bath is not just heat, but also work or ergotropy, okay? And this is something which should be, this work should be excluded from the bound on the entropy. And when one calculates the efficiency bound for the machines, it should be taken into account as well. So then we come to the conclusion that whatever the source that energizes our machine is, how much time? 5 minutes, okay. All we need to see to it is that if we receive ergotropy or work from the bath, we have to fully use it as work. Well, this is natural. And we have to minimize the heat which is dumped into the cold bath, okay? But we should not insist on reversibility, i.e. delta S equals 0, because delta S equals 0 has nothing to do, I repeat, with the amount of work or ergotropy which we receive from the bath, okay? Now, if you make the mistake, as many people do, and you associate the condition for maximum efficiency with reversibility, i.e. delta S equals 0, you can get nonsense. And here I will show you what I mean by this. Okay, so here you see the Carnot bound, okay. This is efficiency versus the squeezing of the bath with which we interact, okay? So the Carnot bound is independent of that, but this red curve is our result, okay? Which, as you can see, can go above Carnot when squeezing becomes strong. But this only means that it stops being a heat engine. It starts being a mechanical engine, okay? And for a mechanical engine, there is no problem to convert work into work with an efficiency up to unity. However, if you insist on attributing all this energy to heat, as some people do, then, and I would be embarrassed to have this in press, but they did, okay? You get the blue curve, which goes above 1. Okay, now this is nonsense, because efficiency above 1 means that you get more energy out that you put in, okay? So this is not the way to go. Now let me, I don't have much time, but let me dwell on something which we are now thinking of doing experimentally with NIR here, and this is based on a paper that we've written with Marlon Scully recently. And that has to do with a two-level system that acts as a maser or as a heat machine, okay? It's the simplest heat machine you can imagine. Just a two-level working fluid connected to hot and cold bath. Now, we previously did a classical analysis or semi-classical analysis of that, in which we modulated this level distance by an external field. But such modulation is the classical limit of what one would get from a quantum mechanical analysis, in which you start off, now this is the Fock state ladder, okay? You start off your signal mode, if you like the piston mode, you start off in a coherent state. And there is a good reason why you started in a coherent state. And then it gets amplified at the expense of the heat bath, okay? But as it gets amplified, it also gets heated up. And the question is, what portion is attributed to heat and which portion is attributed to work? And with this I will conclude. So this is the result. The result is that in the phase space, okay, This is the state of the piston or the signal you started from, okay? It was coherent. If it were not coherent, if it were vacuum, you would only get heat. And that would be a disaster. That would not be an engine at all. But if you start in a coherent state, then as it gets amplified, all this part is associated with work or ergotropy, which is gained by the piston. But the yellow circle corresponds to the heating of the distribution, okay, and is associated with heat. Now, you can see by decomposing the amplified energy into heat and work that, in fact, things only improve as you approach the classical limit. In the quantum limit, the efficiency is very poor. You can see it here. But as you approach the classical limit of high coherent states, you attain the Carnot efficiency. All right? Now, what does this mean? It is actually a counter-argument to Seifert and those that think that off-diagonal elements, okay, are a quantum source of work. Because in fact, off-diagonal elements is what is inherent in a coherent state when you decompose it in the Fock basis, okay? And the coherent state is the most classical state. So it's in fact, what they attribute to quantumness is in fact pure classicality, okay? So now I can conclude with the following comments. All right, we have identified heat as the part of energy which is exchanged with a bath that yields entropy change, all right? Unlike the previous assumption that it is the change of total energy. It is not, okay? Now, this is something which is not covered by the second law. The second law doesn't tell us about the decomposition between heat and work, because the second law does not deal with mechanical work, okay? So now we, from these considerations, we can infer the maximum efficiency of so-called quantum engines, all right, as the point where loss or heat dumped into the cold bath is minimal. But it does not imply reversibility as Carnot engines do, okay? Now, it can go above Carnot, but then it is a mechanical engine, and again, there is no contradiction to thermodynamics, nor is there something which is uniquely quantum. And this is really the crucial point, which is the last point. There are only two features which play a role in what determines the efficiency or the power of machines. It's non-passivity or ergotropy and temperature or entropy. Now, neither is exclusively quantum. They both have quantum counterparts or classical counterparts, and there is no principal difference between those. This applies to features such as the coherence of the piston or the signal mode, the squeezing of the working fluid or the piston. These are all features which can be both classical or quantum mechanical. The only resource which we could identify as purely quantum is when you take many such machines, okay, and you quantum correlate them. This is the case of the decay model, which I have no time to discuss here, but if you have many atoms that cooperatively interact with the bath, you can boost the power, not the efficiency, but you can boost the power output, and that is associated with the quantum degeneracy of decay states. This is something which is indeed genuinely quantum, but for single systems, we have still no indications that there is something which is truly quantum in this business. Thank you very much.
Thank you.